Hello and welcome back what has quickly become one of my favorite parts of the week. Today is Wednesday, November 3rd, and being a Wednesday, we are going to be talking about calculus today. The last few weeks, we've been focusing a lot on functions and extrema, and we've figured out how to find the minimums and maximums of functions, and we've analyzed functions to what seems like as much as we possibly could. I'm here to spoil it to you that we have not finished analyzing functions in graph just yet. We'll be wrapping that up today, though. So if this hasn't been your favorite topic, yay. We'll be moving on to other things. So today we're talking about curve sketching and optimization, both of which may seem a little bit strange and unrelated to each other, but they're going to use a lot of the things that we've learned about functions and extrema to help us solve some sorts of questions. So without further ado, we're just going to jump right into it. So we're going to start out actually with just a simple practice problem. So this is going to review a lot of the things that we've learned about extrema. And simply all we want to find are these quantities on the right, critical points, intervals that are increasing, decreasing, etc. And knowing how to find these is going to be critical in the future. So let's start with the critical points. We know that critical points occur when the first derivative equals 0 or dne. Well, what is the first derivative of a function? We have the graph of f of x. By definition, the first derivative is the slope of the tangent line at some point x. So we want the slope of that tangent line to be 0 or dne. Well, if slope is rise or over run, and let's just say we're looking when the slope is equal to 0, we would get slope equals 0 when the rise equals 0, which means that we would look for a horizontal tangent line. For dne, that occurs when the run is 0, because then we're doing rise divided by run equals 0, and then we're dividing by 0. That's not good. So that occurs when we have a vertical tangent line. So we can just look at this graph and see if at any point, just choose like this random point here, the tangent line looks something like that, and we're like, okay, the slope of that line that I just drew, that is neither 0 nor dne, so that's not a critical point. And it should be pretty easy to see that there are no points in which the tangent line is vertical, right? We can just put this vertical line in different places and we see that it's not tangent to anything. So really, we don't have to worry about that. However, if we're looking for horizontal tangent lines, there are plenty. Over here at x equals -4, we see that there is a tangent line at x equals -4, and that appears to be tangent. So that should be a critical point. Similarly, at x equals 0, the tangent line seems to be horizontal, so we expect that to be a critical point. And then remember at x equals -4, this felt like the lowest point on the graph. It was like a minimum. So, and we should remember that minima are critical points. So we see at x equals 4, we have this other sort of minimum looking thing. And sure enough, it has a horizontal tangent line there. So let's just write those down. -4, 0, 4. But wait, those are the obvious ones, right? This is like a valley, this is like a hill, this is like another valley. There's one that's hidden in there that we forgot. Remember, we're looking at horizontal tangent lines. And sure enough, at x equals 2, we're at this point here. And if you consider the tangent lines as we approach that point, you can see that slowly and surely, our tangent line will reach 0. So indeed, 2 is also a critical point. So that's how we find our critical points. Take the first derivative of the function, set it equal to 0. It's really easy when we have like f of x equals x squared plus 2, because we just find the first derivative and set it equal to 0. But when we're given a graph, we have to think, what should the tangent line look like? And that's how we get these values. Okay, let's look at increasing intervals. So increasing intervals, I'll just group these together and I'll write it here. So increasing we want f prime of x to be greater than 0. We want the slope of the tangent line to be positive. And for decreasing, we want f prime of x to be less than 0. We want the tangent lines to be negative slope. So let's just start traversing our graph and seeing what the tangent line looks like. So before x equals -4, it seems that our tangent lines have a negative slope. So then, when does it change? Well, as we get past x equals 4, we know the tangent line at x equals -4 is 0. As we go slowly past that, we can see that the tangent lines have positive slope. So the first interval is from -infinity to -4. It may not be -infinity, like we don't know what the function does elsewhere, but since this is just what we're given, we'll just say -infinity to -4 just because. But the point is, at -4, the slopes start changing. So it's positive, 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 positive until we reach x equals 0. Then at x equals 0, we said that the slope is 0. So that's fine. We should still check if after x equals 0, are we still increasing or do we go decreasing? And sure enough, the slope of these lines are negative. So we had this interval. I probably shouldn't use the color black. We have this interval here in which the function is increasing. So that would be -4, 0. Okay, still got to keep on going. We have to consider all intervals. So here we're at 0. Tangent line negative, 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 negative. We reach tangent line equals 0 at x equals 2. Good. So now we have to check, are we still decreasing after 2 or are we increasing? And we can see that after 2, our tangent lines are still negative slope. And then we reach x equals 4, in which again we're at 0. So then we want to see, do we continue decreasing? And in this case, no, our tangent lines after 4 are positive. So from the interval x equals 0 to x equals 4, we're decreasing. And you can sort of think about this as like ski slopes, right? If I start at the top of this slope here, at the top of my interval, I would be able to ski down this path without any issues. I just go straight down. Well, not straight down, but I can ski down this path, right? And similarly, from -infinity to -4, I could ski down that little path. However, from -4 to 0, I can't start at the bottom. Like, I can't start here and then ski upwards. That would be a feat of physics if I could. So yeah, think about skiing. That'll help. Okay, so we said x equals 0 to x equals 4, we're decreasing. So we're going to add that to our decreasing intervals. So we'll just union our intervals together. So this U looking thing is our symbol for union. That just means we're putting it together. And then we have one more interval to consider, and that's what happens when we start at x equals 4. So we're at 0, and then we can see that our tangent lines are increasing. So we will go to increasing, and we will union that with 4, infinity. And we've covered all of our intervals. Every single point from -infinity to infinity is in one of these intervals. We haven't left any points out, so we're in good shape. Cool. So next we want to find the relative max and relative min. We should remember that the relative max and min can only occur at our critical points. So we have 4 points that we need to look at because we've already found our critical points. And relative max is when the I should probably write this. Relative max and min. I guess I'll group them together. So max, f prime goes from positive to negative. Whoops, I should probably just use the sign. And then for min, f prime goes from negative to positive. So this means if we have a maximum, a relative maximum, on the left-hand side of that maximum, f prime should be positive, and on the right-hand side, it should be negative. Okay, so let's just look at our critical points. We'll start at -4. We're here. To the left of it, f prime is negative. You know what? Let's even partition it out a little bit. I'll just partition it by where our intervals changed. So here we said that f prime is less than 0. To the right of it, we said f prime is greater than 0. For this interval, we said f prime is less than 0. And after, we said f prime is greater than 0. Okay, so here, to the left, we're less than 0. To the right, we're greater than 0. So that would be, according to our definition here, a relative min. So this occurs x equals -4. Okay, now let's look at the next critical point at 0. So we're here. To the left of it, f prime is positive. To the right, f prime is negative. So by our definition, that's a max. So x equals 0 goes there. Cool. Let's check x equals 4 next. We're here. To the left, f prime is less than 0. To the right, f prime is greater than 0. By our definition, that's a min, so we'll add that along here. And finally, we have to check x equals 2. We're here. To the left of it, f prime is less than 0, and to the right of it, f prime is also less than 0. So that's neither a max nor a min, so we just don't include that in our answer. Cool. So next we have to find points of inflection. So points of inflection occur, let me write this here. Points of inflection, that's our abbreviation, occur when the second derivative equals 0, or where f double prime is changing signs, I'll just say. Actually, that's not true. I'm thinking of something else. Disregard that. So where the second derivative is equal to 0. Okay, so let's take a look at it. For this, we're looking at concavity. So concavity, it really comes down to how you see the graph. And you should be thinking, I explained this in our lesson on concavity, that you think about concavity as going into a cave. So for this section of the graph here, or like for most of the left-hand part, would I go into a cave like this? If this is like, I guess I should explain what this line represents. You can imagine that this is like a wall, right? So this is like the boundary of a cave. So would a cave make more sense if we were to enter it here, and this is like the field of the cave, or if we entered it here and then it's like randomly protruding in that fashion? And it should make sense this way, right? We have this like bowl shape, and that's like the shape of a cave. So yeah, think about, you're looking for the bowl shape and which way the bowl is pointing, and in this case, the bowl is pointing upwards. So in fact, up to here, it's pointing upwards. So in this case, f double prime is greater than 0. Concavity is concave up. The bowl is pointing upwards. And then we get to this section when the bowl part is starting to point downwards. And well, where exactly does that end? That would be a point of curiosity. Well, let's see. What if we just keep it until x equals 2? So we're looking at all of this. Well, then you might say, let's just restrict our vision to this portion of the interval. And then if we look at that, the bowl is pointing like this direction, upwards and to the right, but that's still upwards, right? So the concavity changes at x equals 1 here. And we can see that now the bowl is pointing downwards, f double prime is less than 0. So we said from 1 to 2, the bowl is pointing upwards, like that. But let's see if we can extend that interval a little bit more. Let's go until x equals 3. So we're looking at this curve here. Would we say that this is pointing this direction? Maybe, but it's quite symmetric, this curve here. So we could also say like it's pointing in this direction, so that's kind of confusing already. So maybe we're starting to think we can't extend our interval. So let's just check. We extended it from 1 to 2 to 1 to 3. So let's just look at 2 to 3. So we're looking at this section of the curve here, and then you're like, okay, here it's definitely pointing downwards. So for this section, the bowl is pointing upwards, f double prime is greater than 0. And then we said from 2 to 3, we are pointing downwards, so we're good to go there. Let's see, can we extend this a little bit more? Let's try to go to 4. Well, you can see that this shape is very similar to the shape we just encountered here. So you would conclude that, no, we can't really extend it further. We can look at from 3 to 4, and you see that that bowl is pointing upwards. So let's just look from 2 to 3. This bowl, we said, is pointing downwards. So we say here, f double prime less than 0. Finally, from 3 to 4, that's pointing upwards. 4 to 5, that's also pointing upwards. So like 3 to 5 and onwards, it's pointing upwards. So here we say f double prime greater than 0. Okay, so what was the point of all of that? The point is that these points of inflection occur when the second derivative equals 0. And in basically all of these cases, it's where f double prime changed signs. We highlighted this -1 here. To the left of it, f double prime is greater than 0. To the right of it, it's less than 0. So here it's equal to 0, and f double prime changes signs. And in fact, at all of these points, it changes signs from positive to negative, or negative to positive. So these blue points are our points of inflection. X equals -1, 1, 2, 3. Now finally, for concave up and concave down, we want some intervals. And lucky for us, we already provided these intervals. So I'll just write them out so we're clear on it. Concave up is -infinity to -1. We union that with 1 to 2. And we union that with 3 to infinity. And for concave down, this is -1 to 1. And we union that with 2 to 3. Okay, hefty problem for sure. Covered a lot of stuff, but knowing all of this will be super helpful when we move on to our next section, which is curve sketching. So to a lot of students in calculus, curve sketching is a little bit strange. They don't really see the point of it. This was actually one of my favorite topics in calculus. I think it's really cool, and you'll see why very quickly. Basically, we're just going to be given a function, any function for the most part, and just given that function, by the end of this lesson, we'll be able to draw what it looks like, which is a pretty cool party trick. I'm kidding. I don't know what kind of parties would people be amazed by your ability to draw functions, but nonetheless, we're going to learn how to do it, so let's jump into it. So I'm going to give you some tips on how to do this, and then we're just going to dive headfirst into examples. So here are my tips. First, you want to determine the domain and the range of the function. So we're usually, I think basically all of curve sketching is on the xy plane. So you want to see, does my function accept all values of x, or is the domain restricted in any ways? Domain, not too much that happens, maybe with like periodic functions where things repeat a lot. We'll see an example of that in just a moment. Range, that's also range is more common to be restricted. Range is what the function outputs. So it could be like all real values in which we can get any possible y value, sometimes our y values are constricted, so our range is constricted. So determining these two can be quite helpful. Next, we're going to determine our intercepts, asymptotes, and symmetry. We won't be focusing too much on symmetry. I'll sort of like hold your hand through it because we haven't talked about it much, but we should be feeling comfortable with intercepts and asymptotes. So intercepts, the y-intercept, we set x equal to 0 and just solve the function. For y-intercept, we set the function equal to 0, solve for x. Asymptotes, we've learned a little bit about that, about like looking at the denominator of functions when it's equal to 0, things like that. Denominator equals 0 gives us the vertical asymptotes. Horizontal asymptotes occur when the limit as your variable approaches infinity gets to some value for your function. I'll explain that in more detail in just a moment. Third, you want to compute the first derivative and second derivative of your function, and then find the x values for where f prime of x and f double prime of x equals 0 or dne. Just computing these derivatives and getting these values are going to be super helpful. We know that doing this will give us our critical values. It'll help us to determine our maxima, our minima. F prime of x will tell us where our function is increasing, decreasing. F double prime of x will tell us concavity. So you can see just doing this will piece a lot of things together. And lastly, just use what you know about extrema, how like the sign of f prime of x changes. And also about points of inflection, how f double prime changes. Using those, what we know about those, we can make some good conclusions and draw our graph. So here is my toolkit for curve sketching. There's about 6-7 things that you want to do almost always when you're curve sketching. These are the things you want to find. So x-intercepts. Like I said, solve for x by setting f of x equal to 0, and then you just solve for x. Your y-intercepts, you solve the function when x equals 0. Vertical asymptotes. Those occur when the denominator of f of x equals 0, or simply when the function does not exist in some other context. Horizontal asymptotes. To do that, we take the limit as x approaches positive and negative infinity of the function, and that'll give us the horizontal asymptotes. Critical numbers, we can do that by taking the first derivative of our function, setting it equal to 0 or dne. Points of inflection, double derivative, set it equal to 0 or dne. For intervals, this helps in like breaking up what you're drawing into like smaller chunks, and you can do that by choosing your asymptotes, critical numbers, and points of inflection as your stop points of how they define your intervals. Might be a little confusing, but let's just get into an example. So we're going to draw the graph of this, 2 times x squared minus 9 over x squared minus 4. And immediately you might be like, I have no idea what that graph looks like. And yeah, it's definitely a interesting graph, not one that you would normally expect, but let's just see what it looks like. So the first thing I like to do is compute the first and second derivative. So let's do that. First, I'm just going to simplify the numerator a little bit. I don't like to have this multiplication because then I worry about like product rule and stuff like that. So here it's all nice and simple. Okay, so f prime of x. How are we going to get this? This is our function. We need to take the derivative of it. It looks messy, and it's going to require the quotient rule. So let's do the quotient rule. Low, x squared minus 4, times the derivative of high, d dx of 2x squared minus 18, minus high 2x squared minus 18, times the derivative of low, x squared minus 4. All of this over low, x squared minus 4 quantity squared. Okay, let's compute this out. X squared minus 4, derivative of 2x squared minus 18 is 4x, minus 2x squared minus 18, derivative of x squared minus 4 is 2x. All of this divided by x squared minus 4 quantity squared. Beautiful. And you can do the algebra, but I'll save us some time. And this should hopefully get 20x over x squared minus 4 quantity squared. So that's our first derivative, which will be helpful soon. But first, let's find the second derivative of x. And to do that, we have to take the derivative of this function here. And that looks like quotient rule again. So let's do it again. X squared minus 4 low times the derivative of high is derivative of 20x minus high 20x times derivative of low. That's x squared minus 4 quantity squared. All of this over x squared minus 4 quantity squared, that quantity squared. Goodness me. Okay, let's simplify the numerator. This is x squared minus 4, derivative of 20x is 20, minus 20x. Derivative of this, that's going to use the chain rule. 2 times x squared minus 4 to the power of 1 times the derivative of the inside, which is 2x. Our denominator, we can just multiply our powers and we get x squared minus 4 to the power of 4. If we do some multiplication and some factoring, I'll save us some time here. This should be equal to negative 20 times 3x squared plus 4. All of this over x squared minus 4 cubed. I hope that's right. Yeah, just hopefully it's right. Okay, so now let's list out the things that are important to us. X-intercepts. Y-intercepts. Vertical asymptotes. Horizontal asymptotes. What else do we want? We want our critical numbers. Critical numbers. Our points of inflection. And then maybe we'll consider the domain and our test intervals. Okay, so it's a lot of things, but let's just walk through it one by one, and then we'll see at the end how we can piece everything together. So let's start with x-intercepts. So this occurs where f of x equals 0. So we have f of x equals this. Let's just set it equal to 0 and see what happens. We get 2x squared minus 18 over x squared minus 4 equals 0. So in order for that to happen, our numerator has to equal 0. So this implies 2x squared minus 18 equals 0. That tells us 2x squared equals 18. X squared equals 9. So x equals plus or minus 3. Those are our x-intercepts. Okay, let's do y-intercepts next. Here we want to compute f prime of 0, or f of 0. So that's equal to 2 times 0 squared. We're just plugging in 0 for x. 0 squared minus 4. So that's equal to negative 18 over negative 4. So that's equal to 9 halves. So I'll just write it out. Y-intercept at 0, 9 halves. And then if we go back to here, our x-intercepts, that's just saying 3, 0 is on the graph and negative 3, 0 is on the graph. Awesome. Let's take a look at our vertical asymptotes. So this occurs, according to our toolkit, when the denominator equals 0. So our denominator here is x squared minus 4. So we want x squared minus 4 to equal 0. So we want x squared to equal 4. That tells us x equals 2 and negative 2 are vertical asymptotes. All right, let's do horizontal asymptotes next. Okay, so this will be the limit as x approaches infinity of f of x. So that's equal to the limit as x approaches infinity of, I'll just rewrite the equation. Is that right? Or is it? Yeah, that's right. Okay. And if we remember, last week we talked about limits at infinity. We looked at the highest degree terms of the numerator and denominator. And in this case, the highest degree term is the x squared term, and in the denominator, it's also x squared. So when they're equal, we take the ratio of their coefficients, so this would be 2 over 1, which is equal to 2. So y equals 2 is a horizontal tangent. And you can also do the limit as x approaches negative infinity of f of x, and that will also give 2. Okay, so why is it y? Well, because we're looking at horizontal tangent lines, and horizontal lines are y equals some constant. And also we're seeing the output of our f of x function as x gets really, really large, and the output of this function is a y coordinate. Okay, cool. So we've done this, we've done that, we've done that, we've done that. Now we need to do critical numbers. Okay? Critical numbers. So for this, we want f prime of x to equal 0. So what is f prime of x? Let me just copy it. We've already solved for it here. Copy, paste. We want this to equal 0. So really, we want the numerator to equal 0. So we want 20x to equal 0, and that only occurs when x equals 0. Cool. And then, let's see, are there any other ones that we have to consider? Well, yeah, we should consider when f prime of x equals dne. And that occurs when our denominator is equal to 0. So we want x squared minus 4 squared to equal 0, or x squared minus 4 to equal 0, or x to equal plus or minus 2. And you should be like, wait a second, we kind of already did that with vertical asymptotes, and we got x equals 2 and negative 2. So that should be prompting us to think that, okay, even though we have critical numbers here, those aren't going to be any sort of maxima or minima because we have a vertical asymptote there. So the function's not really, there's no value of the function at that point. It's where it's undefined because the denominator equals 0. So we have these critical points, but they're not going to be maxima or minima. Beautiful. Okay, let's do points of inflection next. So this is where f double prime of x equals 0. So what is f double prime of x? That would be this. Copy, paste. So we want this to equal 0, and as we've seen before, we want the numerator to equal 0. And we can divide both sides by negative 20, so that means 3x squared plus 4 should equal 0. So x squared should equal negative 4 over 3, and we should see that there's no real value of x for that to happen. So there are no points of inflection. Cool. And now we can briefly discuss the domain. And you should be thinking like, okay, what values can I plug into here to get like some sort of output? And that's quite a abstract and broad question. And you might be thinking, well, I can literally plug in any value of x and I would be able to do that, right? I just have a function as defined on x. And like, yeah, you can, except we said that when the denominator equals 0, the function's undefined. That occurs at plus or minus 2. So we kind of exclude those. So we can just say something along the lines of all real numbers except x equals positive 2 or plus or minus 2, right? We have vertical asymptotes there, but there's no function value there. All right, and now let's just think of some test intervals. And I'll explain why I call them test intervals in just a moment, but these are just intervals. So for this, we kind of want to break it up at, well, let's see, where do we want to break it up? We can choose asymptotes, critical numbers, points of inflection. Okay, so what are our, we have plus or minus 2, those seem to be the really important ones, right? We had vertical asymptotes there. Here, so that would be where we want to break up our domain. We're only looking at the domain. We don't really care about the horizontal asymptote because we're breaking it up along x values, and this is like a y value. This is a horizontal asymptote. But then there's also the critical value of 0. So we're going to break up our domain into these chunks. So we'll go from negative infinity to negative 2 because that's our least important value. And then we'll union that with, well, we're not even going to union it. We're just going to enumerate our intervals. So these are the 4 intervals that I claim are important. And if you put them all together, we will get negative infinity to infinity, right? Here we stop at negative 2, but the next interval we start at negative 2. So we've broken up our domain into these intervals, and they're stopped at our important points. Negative 2 is a critical value, and it's a vertical tangent line. 0 is a critical value. 2 is a vertical tangent line, or vertical asymptote, sorry. So those are our 4 test intervals. And I call them test intervals because we want to compute f prime and f double prime in these intervals so that we know how the function is increasing or decreasing. And we know that that function will always be either increasing or decreasing because the intervals are broken up at our critical points, which is where the first derivative equals 0, which is where the function could potentially change. So here I like to make a table. First, we'll look at the interval. Then we'll take a test value. Then we'll compute f prime of x, which is equal to 20x over x squared minus 4. And we'll look at the sign of that, because that's what's most important. Then we'll compute f double prime of x, which is equal to, I have it here, all of this over x squared minus 4 to the cube. Okay, so that's our next value. And then finally, we'll make some conclusions. Okay, so you can see doing this problem is multi-step. We've solved for so many different things. Now we're going to start to piece them together, and after we build this table, we'll have enough information to sketch the graph. So, interval negative infinity to negative 2, negative 2 to 0, 0 to 2, 2 to infinity. So for our test value, we want the test value to be within the range. So I like to choose smaller values because they're easier to work with. So for here, I'll choose negative 3. For this interval, I'll choose negative 1. For the next one, x equals 1. For the last one, x equals 3. So now we'll compute f prime of x for each of these. So this is equal to 20 times negative 3. All of this over negative 3 squared minus 4 squared. So let's just briefly analyze this. This denominator, we can think about negative 3 squared as 9 minus 4, 5 squared, 25. But really, the important thing to see here is that we're squaring something in the denominator. So no matter what this value is, the denominator will always be positive, because when you square anything, it's going to be positive, as long as that anything is a real number, and we're working with real numbers. So the denominator is always positive. Our numerator is a positive times a negative, which would be negative. So negative divided by a positive is a negative, so it's less than 0. Okay, let's do x equals -1 next. 20 times -1, all of this over, -1 squared minus 4 quantity squared. And same thing here, numerator is going to be negative, denominator is going to be positive, so this is less than 0. Let's do the next one, 20 times 1, all of this over, 1 squared minus 4 squared. Denominator is positive as always, but now the numerator is also positive. 20 times 1 is positive, so positive divided by positive is positive, so that's greater than 0. Finally, when x equals 3, we have 20 times 3, all of this over, 3 squared minus 4 squared. Again, denominator is positive, numerator is positive, so the division will also be positive, greater than 0. Cool. So we've found the signs of f prime. I just like to label what the signs look like. So I do minus and plus signs. It just helps me visualize it a little bit better. Great, so now we have to do the same thing, but for f double prime of x. So here, I'll write out the first one because it's going to take a really long time to write everything out every single time. So this is divided by -3 squared minus 4 cubed. So now we have to be a little bit careful. The denominator is cubed, so that could be positive or negative. So -3 squared is 9, minus 4 is 5, so 5 cubed is positive. Our numerator, this is a positive term. Plus 4 will also make it positive. And basically, we can see that whatever is in this parentheses will always be positive because we have 3 times a positive number. It'll be positive when it's squared, and we're adding to it, so this will always be positive. And this is negative, so actually our numerator will always be negative. So we have a negative divided by a positive. This will be less than 0. Okay. For these last three, I'm just going to write out the signs. You can do it on your own time, just for the sake of time. So the first one is negative. This one will be positive. This one will be positive. This one will be negative. All right, so now we're going to make some conclusions based off of what we learned about f prime of x and f double prime of x on these intervals. So for the first interval, f prime of x is negative, so it's decreasing. And f double prime is negative, which means that it's concave down. Second one, f prime of x is negative, so we're decreasing. And now concave up, because f double prime is positive. Next one, both of them are positive. So f prime of x is positive, tells us that we're increasing. And then f double prime being positive tells us that we're concave up. And lastly, we are increasing and concave down. Okay, now we have a ton of information. We're going to put it all together. Let me add a new page. So, I'm going to make this pretty big. Okay, so we draw our axes here. So, first thing you want to do is just sort of plot all of the important things. I realize that those lines aren't very well drawn. Let me try again. That looks fairly vertical. That looks better. Okay, so this is our x-axis, this is our y-axis. So we want to plot things that we're pretty confident on. So let's start by plotting our intercepts. That's what we solved for first. So we know that our graph intersects the x-axis at 3, 0, and negative 3 comma 0. So we'll plot those. And we know it intersects the y-axis at 0 comma 9 halves. So we don't have to worry about like drawing tick marks and everything. We'll sort of estimate it. So let's just say this is a point, negative 3 comma 0. I'll just write it above it for now. And then across on the same side, it's like 3 comma 0, right? And then we had 0 comma 9 halves. So that's somewhere up here. This is 0 comma 9 halves. It's not to scale, but it's good enough for our purposes. Okay, so next, what do we solve for next? We have vertical asymptotes and horizontal asymptotes. So vertical asymptotes at x equals 2 and negative 2, and then horizontal at y equals 2. So let's deal with the vertical asymptotes first. Change my thickness a little bit, and we'll make them dotted. So vertical asymptote at positive 2. So I will represent that as a positive, or as a dotted line, and it should be to the left of this point, because this is at 3 comma 0. We want our asymptote at 2 comma 0, or it should be at x equals 2. So something like this. And then we also had a vertical asymptote at x equals negative 2. So something like that should suffice as well. We had a horizontal asymptote at x equals, or at y equals 2. So here we're at the point 0 comma 9 halves, which is 4.5. So our horizontal asymptote should be a little bit below that, something like this. Ah, that didn't work. There we go. So now we've sort of partitioned our plane into regions in which we can work in. And we have our asymptotes ready. Okay, so now what do we want to do? We've considered horizontal asymptotes up to there. Now we need to consider our critical numbers and our points of inflection and our test intervals. So let's just look at our intervals. We don't really need to worry about plotting our critical numbers and points of inflection because we only have the x values, we don't have the y values. Since our curve sketching is like an estimation, we'll just make it work. So we can look at our intervals, and you'll notice that our intervals are well represented in our graph. The first one we had is negative infinity to negative 2. So that's down here, and we stop at this vertical asymptote. The second one is negative 2 to 0, so we start at the vertical asymptote, end at the y-axis. 0 to 2 goes from the y-axis to this other vertical asymptote, and 2 to infinity starts at the vertical asymptote, goes onwards. So the first interval, we are decreasing and concave down. So before we even draw it on the plot, what would that look like? So functions that are decreasing usually look like this, or like that, something like that, or like this. Of these three, this one is concave down, this one is concave up, and this is like neither, it's flat. So this is the sort of drawing we want, where it's decreasing and concave down. So we're going to try our best to draw that. And the thing to remember is that this point here is an intercept, which means it intersects the axis at this point. So we want to start, I'll zoom in considerably, we want to start somewhere up here. And remember, this is a horizontal tangent line, so we shouldn't start above or below it, or well, we shouldn't start above it, because if we intersect it, then it's not an asymptote. So we should start very close to it, and sort of draw that decreasing concave down shape, and then approach this other vertical asymptote. We shouldn't touch it. So I'm going to do my best to draw it, and we're going to see what happens. Right, something along the lines of that. So we're in the interval negative infinity to negative 2. It doesn't touch the tangent lines, it approaches them, and we're decreasing and concave down. Beautiful. Let's look at the next interval, -2 to 0. We're decreasing and concave up. So I just erased those, but my drawings were this, this, or this. This we said was concave down. The second one is decreasing, but it's concave up, and this was neither. So this is the kind of drawing we want. Okay, but we also know that this is a y-intercept. So if we were to draw this kind of shape, we have to start from somewhere up here. We can't start from somewhere down here and then do a decreasing function and then somehow reach this point. Even if we were to somehow do that, we would intersect this line, which is an asymptote. So we have to start somewhere up here, and then as we get to 0, we intersect that point. So I'm going to try my best to draw it. Something along the lines of this. Cool. So now we move on to the next interval, 0 to 2. Here, we're increasing and concave up. So we know we start here. We have to be increasing, so we have to go in this direction. And we want it to be concave up, so the curve should be pointing upwards. So putting that all together should look something like this. Awesome. And now we have one more interval to consider, 2 to infinity, where we're increasing and concave down. Okay, so let's just consider what that could look like. When we're increasing, our functions could look like any one of these three now. So for the first one, we're increasing and concave up. For the second one, we're increasing and concave down, and this one is neither. So we want this sort of shape. So we also have that this is a asymptote. So it wouldn't make much sense for us to start somewhere random here and then draw that. That just doesn't make sense because we don't really know what's going on. Like, it could be literally anything then, as long as it's concave down. And when there's guesswork like this involved, sometimes it helps to plot a point. Luckily, we already have a point. We know that the graph must intersect here. So that leaves us with one resort. We have to start somewhere at the bottom, then increase, go upwards, and then reach that tangent line. So that's what we're going to do. Something along the lines of that. And that is our graph. You can see how it's sort of symmetric. And looking at our equation, it makes sense that it would be symmetric. There's nothing that would say that it would be otherwise. And then you can sort of like, if you wanted to erase your tangent, actually, no, don't erase your tangent lines. It'll show to your teacher and your grader that you know what's going on. So that's our graph. I know, it was a really long problem, but we started, what did we start with? We started with this. And just with that, a lot of math, we drew the graph of it, which is pretty amazing. So pat yourself on the back. This was a long question, but we should practice a little bit more. So we're just going to do a couple more examples. I'll kind of speed through it, just so that way we can save a little bit of time. So this is our next graph, a much more complex function. We have a square root term in the denominator. So the first step we did was compute f prime of x. So I'm sort of going to do this on the fly. So we do the low times the derivative of the high, which is 1, plus the high times the derivative of the low. So you can represent the square root as the 1/2 power, and then do the chain rule. And you should get something along the lines of this. All of that over the low, the denominator squared, so that would just cancel out the square root term. So it's along the lines of this. You'll want to rationalize your denominator. Well, actually, let me just walk through this. It'll be helpful, I think. First term stays the same. Here, this 1/2 is being multiplied by the 2x, so those cancel. We have an x and an x, that becomes x squared. And this is to the negative 1/2 power, so that's going to go in the denominator, and that'll be a square root. Am I missing something? Yes, I am missing something. It should not be a plus sign, it should be a minus sign. So this would become minus x squared divided by the square root of x squared plus 5, all of this over x squared plus 5. To get this term to look a little bit nicer, we're going to multiply the entire thing by a form of 1. So that way this cancels with the denominator of this. So we see that this is equal to this times that is simply x squared plus 5. And then this times this is minus x squared. All of this over, we can think of this as x squared plus 5 to the power of 1, and this is x squared plus 5 to the power of 5. So this would be equal to x squared plus 5 to the 3/2 power, and that's equal to 5 over x squared plus 3 to the 5/2 power. Or sorry, 3/2 power, yeah. So that's f prime of x. Next we want f double prime of x. And you can do your product or your quotient rule, practice it for fun. I'm gonna save us some time here. This should be negative 15x over x squared plus 5 to the 5/2 power. I encourage you to do that derivative on your own. It'll be really good practice. Okay, let's do our list. X-intercepts. This occurs where f of x equals 0. So we want the numerator to equal 0, which is just x. So we want x to equal 0. So that's our x-intercept. Y-intercept. That is f of 0. So we plug in 0 for x, and we get 0 divided by the square root of 0 squared plus 5. Our numerator is 0, so this equals 0. So we can just write some coordinates for this. The x-intercept, x equals 0, and the y value is 0, because that's what an x-intercept is. Here the x value is 0, and the y value is also 0. So we have an intercept at the origin, basically. That is all of our intercepts. Beautiful. Now we consider vertical tangent lines, or vertical asymptotes. I don't know why I'm saying tangent lines so much. I'm just so used to first derivative. Anyways, this occurs when our denominator is 0. So x squared plus 5 equals 0. If we square both sides, we want x squared plus 5 to equal 0, which is where x squared equals negative 5. And this should tell us that there are none. There are no vertical asymptotes, because x squared will never equal negative 5 when we're dealing with real numbers. All right, add a page. These are long problems. Horizontal asymptotes. For this, we want to take the limit as x approaches infinity of f of x. So I'll write it out. Square root of x squared plus 5. Okay, so how are we going to do this? We have, if you remember back to last week when we were learning about limits at infinity, one of the first things I did was multiplied by a form of 1 to get all of like the x terms in denominators. So we're going to do a very similar thing. And in this case, we're looking at the highest degree term, which is this x squared. We're going to ignore it being square rooted for the moment, but we sort of want to multiply by 1 over x squared times 1 over x squared. And we're going to multiply that by the square root of it. So that way this goes within the square root. And doing this will give us the limit as x approaches infinity of x times square root of 1 over x squared. All of this over. This distributes into here, so we get 1 plus 5 over x squared. And we can see that the square root of 1 over x squared is equal to 1 over x. So this is x times 1 over x. All of this divided by 1 plus 5 over x squared. So this is equal to limit x infinity of 1 over 5 over x squared. And now we can see what really happens. As x gets really, really large, this 5 over x squared terms is 5 over a really, really huge number, which is basically 0. So then we have the square root of 1 plus that very, very tiny number, which is basically 1. So we get that this is equal to 1 over the square root of 1, and that's equal to 1. But I was a little careless. Square root of 1 could be positive or negative, so we specify that here, plus or minus 1. And these are our horizontal asymptotes. So I'll just write them out. Y equals plus or minus 1. All right. Now let's take a look at our critical values. Critical numbers. And this is where f prime of x equals 0. Okay. I guess I made a little mistake here. There should be x squared plus 5. Anyways, where is the selection tool? Or DNE. Okay. So we want, what do we want? We want this to equal 0 or DNE. So this equals 0 when the numerator is 0. So that just never happens. So we can cross that out. And it equals DNE when x squared plus 5 to the 3 halves power equals 0. So this tells us that x squared plus 5 should equal 0. X squared equals negative 5. And that never happens. So there are no critical values for when x prime or when f prime equals DNE. So we just say there are no critical values. Okay, so that might be a little bit confusing. How can we have no critical values? Well, it happens. It just happens. Okay, points of inflection are next, and this occurs where the second derivative is equal to 0. So f double prime of x, I'll just rewrite it. This is negative 15x over x squared plus 5 to the 5 halves. And we want this to equal to 0, so f prime of x equals 0 when the numerator equals 0. And we can see here that this occurs when x equals 0. And really, we saw from before, when x equals 0, we're at the point 0, 0. So we can just label this 0, 0. Cool. So now let's consider our, let's consider the domain. Well, what are the things of interest? We don't really have any vertical asymptotes, critical values. We can plug literally anything into here and we'll get something useful. So there's really nothing to worry about. So our domain is all real numbers. This is the mathematical symbol for all real numbers. It's a fancy R. So hopefully that's known, or if not, you learned it. Math is really cool in that we use some fancy letters sometimes. Got this one for integers, natural numbers. One of my favorites is Q for rational numbers, but that's besides the point. Now we'll consider our intervals. And you're like, okay, well, we don't really know where to split things up because we didn't have any critical values or vertical asymptotes. But we do have this nice little point of inflection, so that might be a nice place to split things up. So let's just consider from negative infinity to 0 and 0 to infinity. So now we create our table, interval, test value, f prime of x, I forgot what the equation is, f double prime of x, and then conclusion. Let me just get these values, or these equations. X squared plus 5 to the 5 halves. I believe this had x squared plus 5 to the 3 halves in the denominator, and the numerator was 5. Okay. So that's our table that we use. It's a bad line. And we have 2 intervals, so a lot less work to be done. Test value, I like to keep it simple, so we'll do x equals -1 here. Make sure your test value is within your interval. So indeed, -1 is in this interval. Similarly, 1 is in this interval, so that's good. F prime of -1 equals 5 divided by -1 squared plus 5 to the 3 halves. This is positive. -1 squared is positive plus 5 is positive. When we take the 3 halves power, that will also be positive. So positive divided by positive is still positive. So that's a plus sign there. Whoops. Here we do f prime of 1. This is 5 over 1 squared plus 5 to the 3 halves by a very similar logic that will also be positive. Cool. Let's do f double prime. This is -15 times -1 divided by -1 squared plus 5 divided by 5 halves. Our numerator is positive. Our denominator is also positive. This is going to be greater than 0. We'll give it the good old plus sign. And we'll do f double prime of 1. That's -15 times 1. All of this over 1 squared plus 5 to the 5 halves. This is a negative numerator. Our denominator is positive. So this is going to be negative. We'll give that the minus sign. And then we make our conclusion. F prime is positive. F double prime is positive. So we say it's increasing on this interval. And concave up. Second interval, f prime is positive, so we're increasing. F double prime is negative, so we're concave down. So we say increasing and concave down. And now we've done everything. We are ready to sketch it, so let's just do that. Draw some axes. Okay, so what do we have to be concerned about? First of all, we should remember that we have our intercept at the origin, so we'll make that a nice little point there. Let's just scroll back and look through what we did. No vertical asymptotes. We have horizontal asymptotes at y equals plus or minus 1, point of inflection at 0, 0. Okay, so not too much to work with, but let's draw our horizontal asymptotes. So y equals 1 looks something like this. And then y equals -1 looks something like this. Okay. I guess I should probably write that. This is 1, this is -1. Okay, so now we consider our intervals. The first interval is -infinity to 0. So from down here to this axis, we are increasing in concave up on this interval, and we have to intersect here. So if we're increasing, we're going in this direction. So we shouldn't be starting anywhere up here, because if we increase, we'll never be able to reach this point. So we should be starting in this section down here somewhere. And since this is a horizontal tangent line, it makes sense to start very close to it. So we want to be increasing and concave up. I'll use a different color this time. I'm going to do my very best to draw this. something like this. All right, we're within the interval, we're increasing concave up, and we intersected at the correct point. Next interval, 0 to infinity. We're increasing and concave down. So we should probably start here because there's no jump discontinuity there. So we're increasing going in this direction. This is our asymptote, and we're concave down, so our bowl should point this way. So it should look something. I didn't like that. Something like that. That's our graph. And if you scroll back, we've covered everything. We've covered our points of inflection. We can quickly check that here, second derivative is 0. To the left of it, we're concave upwards. To the right, we're concave downwards. So the second derivative is switching. Critical numbers, we don't have any. So do we see any minima or maxima? We don't, which is good. Vertical asymptotes, there are none. Great. Horizontal asymptotes we took care of. Intercepts we're good on. This is looking like a really solid graph, and this is indeed the graph of x divided by x squared plus 5 square root. Awesome. Let's do one more. This time we'll throw in some trig functions. Let me just add a page. So now we have to be a little bit careful with things because we know trig functions are periodic. So with that said, let's just get into it. As always, we are going to start by computing the first derivative. And unfortunately, again, it looks like we're going to have to use the quotient rule. So I'll do it on the fly. Low, d high, derivative of cosine x is negative sine x minus, got that correct this time, high times the derivative of low, derivative of 1 plus sine x is cosine of x. All of this divided by 1 plus sine x, quantity squared. So this is equal to negative sine x minus sine squared of x minus cosine squared of x. All of this divided by 1 plus sine x squared. So we can look at this a little bit closely. We have minus sine squared x plus cosine, or minus cosine squared of x. If we just throw in some parentheses here and make this a plus sign, that's the same thing because now the minus sign distributes. And we're like, hey, sine squared plus cosine squared, I know what that is. That's equal to 1. So this is equal to 1 minus, let's do sine of x minus 1 over 1 plus sine x squared. And you're like, wait a second, this is so close to this. There's a 1 and there's a sine x. So we can factor out, we can do a really similar thing. Throw in some parentheses, change this to a plus sign, and they're equivalent. And we see that this is equal to this in the denominator. So really, this simplifies to negative 1 over 1 plus sine x. I did a little bit of some strange simplifications in there, but you can try it for yourself and hopefully you'll get the same answer. All right, now we do f double prime of x. We can do quotient rule again, but this looks simpler. So low d high derivative of negative 1 is simply 0, minus high is negative 1, d low, that's just cosine of x. All of that over 1 plus sine x, quantity squared. This simplifies down to cosine x over 1 plus sine x, quantity squared. Cool. So we have first derivative, second derivative. Now we go through our checklist. X-intercepts. This occurs when f of x equals 0, and we're dealing with a fraction, so we want our numerator to equal 0. Cosine of x equals 0. And we know this happens at a lot of places. This occurs at x equals plus or minus pi over 2. It also occurs at x equals plus or minus 3 pi over 2, and plus or minus 5 pi over 2. A ton of places. It goes on and on. And a good thing to notice is that it's periodic in terms of 2 pi. It takes 2 pi to get to here, and it takes 2 pi to get to there. So this periodicity, I hope that's a word, will come into play very soon. Y-intercepts. For this, we want to compute f of 0. So this is equal to cosine of 0 divided by 1 plus sine of 0. Cosine of 0 is 1. Sine of 0 is 0. So this occurs at 1, so our point is 0, 1. Cool. Next, we need the vertical asymptotes. Okay, so where does that occur? That occurs when denominator equals 0 or 1 plus sine of x equals 0. So that occurs when sine of x equals negative 1. Now, when does that occur? Boy, that's a tricky question. That occurs when x equals, well, like negative pi over 2, 3 pi over 2, 7 pi over 2. So again, we see 2 pi to get to there, 2 pi to get to there. That periodicity comes into play. Now, you might be noticing something. You're like, hey, wait a second, this negative pi over 2, I've seen that before. It's right here. And then there's this 3 pi over 2, and that's also here. You're like, wait a second, how can we have both an x-intercept and a vertical asymptote? And my claim to you is that these values are actually our vertical asymptotes and not x-intercepts. And my challenge for you is to figure out why that's true. So take some time and try to figure that out for yourself. But these are going to be our asymptotes. And note that this list continues on. Okay, horizontal asymptotes. For this, we take the limit as x approaches infinity of cosine x over 1 plus sine x. And this is very, very hard to evaluate because as x approaches infinity, we don't really know what cosine of x is because cosine of x looks like this. It oscillates. So it doesn't approach anything. So we simply say there are none. There are no horizontal asymptotes. Okay? Next, we're looking at critical numbers. So this occurs where f prime of x equals 0 or dne. So that means we want negative 1 over 1 plus sine x to equal 0. And that just does not occur ever. So this will just say never. But if we want this to be equal to dne, then we want 1 plus sine x to equal 0. And as we just solved for, this occurs when x equals negative pi over 2, 3 pi over 2, 7 pi over 2. So you'll see it's very common for people not to solve for f prime of x equals dne because doing that is nearly equivalent to finding our vertical asymptotes. So we don't really plot these whatsoever, but I do that just for the sake of practice. So those are our critical numbers. Points of inflection is next. So that would be where our second derivative is equal to 0. So we want cosine of x over 1 plus sine x to equal sine x squared to equal 0. So we want cosine of x to equal 0. That happens at a ton of places. Plus or minus 3 pi over 2. Plus or minus, wait. Did I do this correctly? By the way, here I made a mistake. The periodicity, like this jumping is not 2 pi, this is pi. But here it's 2 pi, and that's going to be critical. But going back to this, we see that we already solved for cosine of x equals 0. So we note that the points of inflection are all of our x-intercepts. And also none of the vertical asymptotes. Because remember, there is some overlap. Okay? So we've done that, we're in good shape. Okay, so now let's return to our function. We had f of x equals, shoot, I forgot what it was, cosine x over 1 plus sine x. Okay, so we should remember that cosine of x is periodic with period 2 pi, and this one, and sine x is periodic with period 2 pi as well. So we should restrict our vision to an interval that is of size 2 pi. And if we look at our calculations, we need to think what would be a logical thing to look at. And I pointed out here with the vertical asymptotes that you have to jump 2 pi to get to each new vertical asymptote. So let's just take a look at one of these intervals, negative pi over 2 to 3 pi over 2, and see what happens. We'll consider negative pi over 2 to 3 pi over 2, and then we'll see if things repeat. Okay, so within this interval, we should break it up into subintervals, as we did previously. So are there any points within this interval that seem important? Well, here there's a positive pi over 2, which seems important, so that might be useful, but that's just an intercept. We don't really care about intercepts. Asymptotes, that's how we defined our interval, so that doesn't really matter. A horizontal asymptote, there are none. Here, none. Points of inflection, we see that positive pi over 2 again, and we can see that out of all the points of inflection, there's only one that lies within our interval. So we'll break it up at that point. So we will create our chart, and I'll just write the intervals first that we're going to break it up on. 3 pi over 2. So those are the intervals we're going to work with. And again, we'll do a very similar thing to before. We'll choose our test value. We'll compute f prime of x, which is equal to, gotta scroll back, negative 1 over 1 plus sine x. We'll compute f double prime of x. That is equal to cosine x over 1 plus sine x, quantity squared, and then finally we'll make our conclusions. So lots to do. Choosing the test value is my favorite part. Just got to look within this interval and choose something nice. I like the value 0. And then for the second one, a little bit less nice, but we'll choose x equals pi because we're dealing with trig functions. So f prime of 0. This is equal to negative 1 over 1 plus sine of 0. Sine of 0 is equal to 0, so that's less than 0, negative 1 over 1. So we put a negative sign there. F prime of pi, negative 1 over 1 plus sine of pi. That's also equal to 0, so it's 1 plus 0 in the denominator. Same thing, less than 0 gets a minus sign. F double prime of 0. We get cosine of 0 over 1 plus sine of 0 squared. Cosine of 0 is 1. 1 plus sine of 0 is 1. 1 squared is 1. So that's greater than 0. This gets a good old plus sign. Finally, F double prime of not 0, of pi. That's equal to cosine of pi over 1 plus sine of pi squared. The denominator is pretty easy, that's still 1. Cosine of pi is negative 1, so we're less than 0 there. That gets a negative sign. Now we make our conclusions. First interval. Whoops. f prime is negative, f double prime is positive. We should be saying this is decreasing and concave up. Second interval, f prime is negative and f double prime is negative. So we're decreasing and concave down. And now we put it all together and graph. Axis there, and we draw our vertical asymptotes. So we were at negative pi over 2 and 3 pi over 2. So we'll just say this is negative pi over 2, and 3 pi over 2 should be somewhere here. Okay, and then actually what I'll do is, no, that's fine. All right, now within this interval we'll look at solely. Let's look at our x-intercepts. There's an x-intercept at negative pi over 2, but we said that that was a vertical asymptote, so we don't intersect there. There's one at positive pi over 2, which is within our interval. There's one at positive 3 pi over 2, but that's a vertical asymptote, and those are the only values within our interval. So we intersect at pi over 2 comma 0. So that's actually at the halfway point within our interval. Cool. Y-intercept at 0 comma negative, or 0 comma 1. So that is somewhere here, I suppose. I guess this isn't very much to scale, but it's something like that. Bear with me. Okay, so we plotted that. Vertical asymptotes we took care of within our interval. Horizontal asymptotes, there are none. Critical numbers, those are our vertical asymptotes. Points of inflection, there's one at positive pi over 2, but that's where we broke up our interval, so that should be taken care of. So now we can just take a look at our chart and do some graphing. So, starting from the left side, we are decreasing and concave up. So for decreasing, and we have to get through these 2 points, decreasing looks like this, we should start up here. So that's what we'll do, and we need to make sure we're concave up. So it should look something like this. That's a pretty bad drawing, but it'll work. Next, we reach pi over 2, so that's why we stopped there. Now we are decreasing and concave down. So we have to decrease in this direction and concave down. So it should look something like this. And that's basically it within the interval. Remember, it's periodic. So this function is actually going to it's going to repeat itself multiple times, and I'll just sketch out one more, maybe 2 more. So we have these vertical asymptotes that are within, like, they're back to back, and they're of length 2 pi, and the graph will look very similar to it. We want to make sure we're intersecting at the appropriate x-intercepts, so you can check your work for that. And it's the same graph, and it just continues on and on. And this is due to the periodicity of the trig functions. And yeah, so that's our last example for curve sketching. So we did 3 examples, but they were all pretty hefty, and we got through a lot of things. So yeah, take some time to look it over. Hopefully you've gotten down the process of how to approach these questions. Take the first derivative, take the second derivative, go through our checklist of things that we need: x-intercept, y-intercept, vertical asymptote, horizontal asymptote, critical numbers, points of inflection. Make your intervals here. Making the intervals might be the hardest part, but in order to break it up, I suggest to look at your points of inflection, your critical numbers, and your asymptotes. And remember, it's better to break up your intervals more than less, because if 2 intervals tell you the same thing, like if this first interval tells you to be decreasing and concave up, and your next interval also tells you to be decreasing and concave up, that's fine. That's perfectly okay. It's better to do that than to not break it up as much. All right, so that is curve sketching, which took